In this video, we're going to look at a complication that can occur during acid-catalyzed dehydration. And this is a case where there's a rearrangement involved, okay? All right, so look at the system here. If I label the carbons alpha, beta, and gamma the way I've been doing that all along, and you look at this result here, this acid-catalyzed dehydration, what you see is that the minor product looks like a classic dehydration product. It's occurring, the double bond is located between the alpha, beta, and beta carbons. That's no problem. But if you look at the major product, look where the alkene is here. It looks like it's located between the beta and the gamma carbons. Okay, so this is an unusual case. It seems to violate all the mechanistic principles we established when discussing the mechanism of the dehydration reaction. Okay, so what is happening here? How did this occur? Well, it has to do with the structure of the carbocation intermediate. Let's look at the mechanism. We're going to find that the early stages of this mechanism don't vary from what we discussed previously. In the excuse me. In the first step, we're protonating the alcohol to afford this protonated alcohol, and then we just lose water and produce the carbocation. Okay? One thing that this carbocation can do is just lose the hydrogen right here and form the minor product. Okay, but that doesn't seem to be the main thing that's happening here. What's really happening is that the hydrogen is actually shifting over. We call this a hydride shift because the net result is that the hydrogen and the bonding electrons end up moving by one carbon. Okay, when you do this, the hydrogen ends up here. Hydrogen and the electrons in the CH bond end up there. And where the hydrogen used to be, right there, has now become a carbocation. Okay? All right. Now you may wonder, why does this happen? Well, look at the structure of the two carbocations. This carbocation here is secondary. This carbocation is tertiary. All right, so by doing this 1,2 hydride shift, we've increased the stability of the carbocation quite a lot. Okay, it's gone from secondary to tertiary, and that's very favorable. All right, so once we have this, we can remove a hydrogen off of what was originally the gamma carbon. Okay, we'll just put the gammas through all the way. So removing a hydrogen off the gamma carbon will give us this. All right. Now, it also might be the case, we don't know this for sure, but this could also just be a minor pathway for this carbocation here as well. We could remove one of the hydrogens off of what was originally the alpha carbon as well. Okay, so I'll put the alphas there. So we could have eliminated one of those hydrogens as well to make the minor product. So there are actually two pathways for making the minor product. One is just the identical to the previous mechanism where there's no rearrangements at all, and the other is competition between elimination to form the tetra-substituted double bond, which you'd expect to be major, over the tri-substituted double bond, which would be minor. Okay. Why does this rearrangement occur? Well, it has to do with how carbocations are stabilized. Recall in the discussion of carbocation structure that carbocations are stabilized by an interaction with the electrons in the adjacent CH bond. Okay, so there's an interaction with these electrons, and this is actually serving to basically weaken this CH bond. And it's very easy for this hydrogen to migrate. Remember when we were looking at those resonance structures, and I think I told you not everybody agrees these are resonance, but you could look at, I'm going to have to draw it over here because of the program here, but okay, if you start looking at this as a, I'll just call that whole group there isopropyl. That group, remember, is that technically an isopropyl group. That this hydrogen isn't as strongly associated with that one carbon as if it were if the carbocation were not there. Okay, so it's kind of feeling some interaction with both that carbon and the carbon adjacent to it. All right, so because of this hyperconjugation, the net effect is that you're making it very easy for this hydrogen to migrate. This process occurs, the 1,2 hydride shift, with a very minimal degree of activation energy. Okay? All right, we call this a 1,2 hydride shift. We're getting a lot of labels here. Let me just redraw this here. Okay, so we're going to label the carbocation carbon is 1, and the adjacent carbon that's where the hydrogen is shifting is 2. And what you see here is that in the 1,2 hydride shift, the hydride moves off of carbon 2 and goes to carbon 1. The location of the carbocation goes from carbon 1 to carbon 2. Okay, and that's essentially the fundamental thing you want to remember about these hydride shifts. Okay, we can also shift carbons. Here's an even more unusual result. An attempt to dehydrate this compound under acid catalyzed conditions. If we look at the only beta hydrogens are on this methyl group, and this is actually producing only a very minor component of this reaction. What we see here is actually the connectivity of the product has actually changed quite a bit. If we look at this carbon, I'm going to put an asterisk on. There's 3 methyl groups there. Now this carbon corresponds to it in the other 2 products, but you see there's only either 2 methyl groups or a methyl group and an alkene. Okay? All right, so the carbon skeleton has changed in this process, and this is due to a similar phenomenon, except we don't have any hydrogens we can shift in this compound. We can only shift alkyl groups. All right? So what happens here is this reaction, again, starts off as before. In the early stages, we protonate the alcohol, lose water to get a carbocation. Okay, one thing the carbocation can do is lose a hydrogen from the methyl group there, and that'll give you the very minor product which retains the carbon skeleton, but the vast majority of this reaction comes from rearranging the carbon skeleton here. Okay, so here we're going to have a 1,2 alkyl shift, and more specifically a 1,2 methyl shift, since the alkyl group that happens to be shifting is a methyl group. And what you see here is that our carbocation also goes from being secondary to tertiary like we saw before. And this is a very favorable process. Remember carbocation stability. Tertiary carbocations are much more stable than secondary carbocations. All right, so the major product comes from eliminating that hydrogen right there off of one of the beta carbons. And the minor product in 33% yield comes from removing one of the hydrogens off one of those methyl groups that I've designated as beta prime. Okay? All right, well, we don't have hydrogens hyperconjugatively stabilizing, like here. We have alkyl groups that are contributing to the hyperconjugative stabilization, and this can happen in much the same way that the hydrogen shifted in the previous slide. Okay, let's look at another hypothetical process. There's another What about the hydride shift? Could we do it? All right, so here's our hydride shift. We're going to move the hydrogen in a 1-2 fashion. Now, is that a good thing to do? We go from a carbocation that's secondary to one that's primary. So this is not going to happen, right? Because it actually is producing the less stable carbocation. It's an energetically unfavorable process. All right, so the net result here is that if we can generate a more stable carbocation by doing either a 1-2 hydride shift or a 1-2 alkyl shift, the process is very likely going to happen. Okay, all right, and that statement is sort of summarized right up there at the top. Okay, if you have the choice of a hydride shift or an alkyl shift, you usually do the hydride shift first. All right, in the previous slide, all of our alkyl groups that could have shifted were just methyl groups. What if we have 3 different groups? All right, so here's a good example of a compound like this. Here we have an ethyl group, a methyl group, and an isopropyl group. All can shift. Okay, so I've redrawn it here with the, so it's not a complete bond line diagram. It's a little clearer here, perhaps, in the structure over to the right. All right, so we can do 3 different 1-2 alkyl shifts in this case. We can shift the ethyl 1-2 to generate this tertiary carbocation. Okay, we can shift the isopropyl group 1-2 to generate this carbocation here, which is also tertiary. And we can generate another tertiary carbocation by doing a methyl shift. Okay, and this carbocation here is also tertiary. So this is a compound, if you tried to dehydrate the alcohol that was a precursor to this carbocation, you'd probably find a very messy reaction from all of these groups migrating. All right, so interestingly, when the alkyl group is part of a ring, like here, the alkyl shift process actually results in a change in the ring size, okay? So if you look at carbon 2, we have a methyl, and we have 2 different CH2 groups that are part of this 4-membered ring. Okay, when we think about the 1-2 shifts that we can do here, we can do a 1-2 methyl shift to produce this compound, or we can do a 1-2 shift of the CH2 of the ring, and we would produce this compound here. Now, if you count the atoms in that ring size, they're actually 5 now, and a better way to draw a 5-membered ring, of course, is as a pentagon, and that's a neater structure right there. Okay, all right, so you might think, what is the more favorable process here? Shifting the methyl group or shifting the CH2 of the strained ring? Well, it turns out that this process or this dehydrations in systems like this actually are very selective. They tend to provide primarily the ring expanded product. And this is, of course, because when you do this one, there's not only formation of a tertiary carbocation, but there's also a relief of angle strain. Okay, when you increase a ring size from 4 to 5, you eliminate some of the a good deal of the angle strain in that process. Here we also have, remember, the carbocations are sp2 hybridized, so this is a kind of a strained system anyway, strained because there's an sp2 carbon in a small ring. Okay? All right, so of these two alkyl shift processes, the one that expands the ring is a lot more favorable than just shifting the methyl. Both result in tertiary carbocations, but the tertiary carbocation that you get from shifting the CH2 of the strained ring is much more stable. Okay, all right, so we're going to end this slide by doing two problems. First one here is we're going to look at these hypothetical shifts and determine if they can happen. All right, so the general rule, remember, is if we can generate a more stable carbocation by doing a 1,2 hydrogen or a 1,2 alkyl shift, that process is very likely going to happen. All right, so what about this first one? It does generate a more stable carbocation, but if you start numbering the carbons, that hydrogen has to transfer off the third carbon, and this is going to not be all that favorable. So we're not going to see this one occur due to the fact that this is a 1,3 hydride shift, not a 1,2 hydride shift. Okay, this one looks remarkably like the other one. As far as carbocation stability goes, we do go from primary to tertiary, which is good. Okay, if we look at what carbon it moved from, it was carbon 2, so this is very likely to occur also. It's a 1,2 alkyl shift. Okay, so this one's going to be quite favorable, and this is very likely. A more stable tertiary carbocation forms via the 1,2 shift, and there's also a relief of angle strain. Okay. Now look at the last one here. The last one involves migrating this CH2 group of the cyclopentane ring over to where the carbocation is. But here we're doing tertiary to secondary. So this is not good, right? Because this is producing a less stable carbocation. All right, but it is a 1,2 alkyl shift. So we're going to predict that this one is not going to go because a tertiary carbocation became a secondary carbocation. Even though it does qualify as a 1,2 alkyl shift, it's not a favorable 1,2 alkyl shift. All right, so here's a classic mechanism problem. Write a mechanism for the following reaction, and this reaction is producing 3 compounds. Okay, and if you look at the 3 compounds, we could probably say that this is going to be our easiest mechanism to write, right? Because no rearrangements have occurred. Every carbon is attached to the same carbon in reactants and products. Here it looks like a methyl has moved. And here it looks like ring size has changed. We've actually gotten to a smaller ring in this case. And this changes in ring size usually refer to or characteristic of 1,2 alkyl shifts occurring through carbocations. Okay. All right. So there's also another clue here, and that's this numbering system. That's telling you what carbon went where, and probably the hardest one to do, and that's the last one. Okay. So what you'll notice here is that carbon 4 moves from carbon 3 to carbon 2. Okay? All right, and it seems like we break the C3-C4 bond completely because there's no bond between 3 and 4 in the product. Okay, so let's think about how we would write this mechanism. All right, so one of the essential first compound you would have to draw, and it's required that you would draw this compound, is the protonated alcohol. Okay. To really show it good, we should take the lone pairs and react them with the strong acid. All right, in step 2, we are going to generate our carbocation, and it's from this carbocation where all of the processes emanate. Okay, so we're going to just remove a hydrogen from this beta carbon right here. And this is going to produce our unrearranged product. This is kind of an uncomplicated dehydration process going from that reactant to that product. Okay? All right, one thing we can do is migrate a methyl group. Okay? So here, our methyl is moving off of this carbon, which I'll asterisk here, and it's moving to the carbon adjacent to it. Okay, and then we just remove the hydrogen. Okay, I'll just have water come in as a base, and that'll afford the methyl migrated product. Okay, all right, so if you look at the carbon that's doing the migrating, this asterisk carbon, there's a methyl, and a CH2 in a ring. Okay, so the final product results from migrating the CH2 of the ring. All right, so here we're migrating this one over to here, and that's forming this product. Okay, and we're removing a hydrogen from the beta carbon relative to that carbocation, and that's affording that product. Okay, let's look at a couple of mistakes that people make here. And I'll just, for example, show them with this ladder process. Okay? When I put a question like this on the exam, a lot of people don't produce the carbocation that I have circled. They produce this carbocation. Okay? And this is wrong. You see, the problem here is that the carbocation has not changed position. Okay, you've migrated the alkyl group, but you've not migrated the carbocation. Yes, you can draw the final product emerging from this carbocation, but this is not the right intermediate. This is the right intermediate. Okay, you have to shift both of them. You have to shift the CH2 group and the position of the carbocation. Okay. Notice that this hydrogen here was not there in the starting material. So your arrows really don't account for where that hydrogen right here came from. Okay. All right, let's look at another common error that people make. Let's just, we'll show it on this pathway, and this is an error that would be common to all of the pathways. All right, so I'm going to redraw this carbocation. Okay. All right, so I have water pulling off the proton. The other acceptable thing that could pull off that proton is the conjugate base of sulfuric acid, so the bisulfite anion is also okay to show. The one thing that's not, you should not show, is hydroxide ion removing this. Okay? And the reason is that this compound here, hydroxide ion, is not present. Okay? These are the only things that we should be showing in our mechanism, and plus the water that you made in step 2. Okay? But there should not be any hydroxide present. And these solutions are very acidic, so the concentration of hydroxide in acidic water is really, really puny. So you should use water or the bisulfite anion to do all of your deprotonations in a mechanism like this, and not hydroxide ion. Okay. All right. So I think this is where this video ends. Yeah, so we're going to look at the dehydrohalogenation process in the next video. Okay?